We're now going to consider relativistic momentum. So one of the postulates of special relativity was that the laws of physics were the same in all reference frames. So we'd expect that with momentum, momentum should be conserved in all reference frames. So let's have a look at this by considering a situation first of all and looking at whether momentum is conserved. So the situation that we're going to consider is two particles which are colliding. So we'll assume in reference frame S, the two particles are moving with equal speed in opposite directions like this. They collide and they move off at the same speed at right angles to their initial direction. Now in reference frame S prime, we're travelling along with one of these particles. So we'll call this one particle A and this one particle B. We're now in the reference frame of particle B. So in this reference frame, particle B is initially at rest and it looks like particle A is travelling towards it. They collide and then they both get the same vertical component of the velocity, and the initial velocity of particle A is equally divided between the two balls. So what we'll do now is we'll analyse this situation and see if momentum is indeed conserved between the two frames. Okay, so here we've sketched out these collisions in the two different frames, in the S frame here and in the primed frame here. I've also jotted down the velocity transform equations. So we will be using that momentum P is equal to the mass times the speed. So let's start by showing that in frame S, momentum is conserved. So in S, P initial is, we've got these two balls A and B. So let's let this direction be the I direction and this direction be our J direction. So we've got MVI that describes ball A, and then with ball B we've got this is equal to minus MVI as it's in the opposite direction, so this is equal to 0. Now afterwards, so P final is equal to this, which has momentum mv, and now it's moving in the j direction, and then this one, ball B, is moving in the negative j direction, so this is minus mvj, which is equal to 0. So we can be happy about this because momentum is conserved. This value, the final momentum, was equal to the initial momentum. Okay, now let's consider what's going on in frame S prime. So in S prime, P initial. So in this frame, ball A is moving, but ball B is stationary because we're now in the frame traveling with ball B. So the initial momentum is going to be equal to mvi, and that's in our I prime direction, and this is our J prime direction. Now what we can do is write vi prime in terms of the velocity back in this frame here. So to do that, we'll need to use this equation here. So this gives us m. Okay, now we will need to substitute in Vx. Vx is the speed of the ball in the unprimed frame. So that is talking about the speed of ball A, our current ball in the unprimed frame. So that's equal to V. So we've got Vx is equal to V. And we'll also need to consider U. U tells us the speed of the frames relative to each other. So our S prime frame is moving with ball B, so U is equal to minus V. So we can substitute these into this equation here. So we've got V minus V over 1 minus, and that's U is equal to minus V times Vx, which is V over C squared. So this is equal to v minus v, that's v plus v. So this is 2mv over 1 plus, because we've got minus times minus, v squared on c squared. So that's our initial momentum in this frame, and ball B isn't moving, so it has no momentum. So to consider our final momentum, let's break this into components. We've got an x component, in each case going this way, and a y component going this way. Now we can see the x components are going in the same direction, while the y components are going in opposite directions. So this tells us that the x components will add together, whereas the y components are going to need to be subtracted from each other, and so will cancel each other out. So in the y direction, P final is equal to 0. So we just need to x direction. Now, these two balls are going to have the same velocity in the x direction. So what we can do is just calculate one of them and then double it. So this will be equal to 2 times vf dash final in the x direction times m will be the final total momentum. So let's work that out. So let's put the 2m out the front, and then we've got this v final x. So we'll be looking at this. So let's consider ball A. So for ball A, Vx, that's the velocity of ball A in the x direction in the unprimed frame. Now we're considering the final state here. So here the ball has 0 velocity in the x direction. So we'll have Vx is equal to 0. And u, that's the relative speed of the two frames. So that hasn't changed from up here. The S prime frame is moving with the speed that ball B had initially. So we can substitute these into this equation here. So we have 0 minus v over 1 minus, now u, which is minus v times 0, so that's 0. So this is equal to 2m minus, that's plus, so this is 2mv divided by 1, so that's 2mv. But now we run into a little bit of a problem. This and this are not equal to the same thing. So this is going to make us sad because momentum is not conserved. So our rules of physics aren't being obeyed in both reference frames. So what can we do about this? Well, it turns out that the problem is actually with how we've defined momentum this way in the relativistic case. It turns out that we can solve our problem by actually defining momentum P as equal to mv over the square root of 1 minus v squared on c squared. Now, some textbooks will write this as this is equal to m times gamma. Personally, I find this rather confusing because in the bottom here, this v squared is talking about the speed of the object. Generally, when we're talking about gamma, we're using it to represent 1 over the square root of 1 minus u squared on c squared, where u is the relative speed of the two frames. So the two frames, not the object that's being described. So I prefer to write the momentum equation this way in the relativistic case. So what we're going to do now is show that by expressing the momentum this way, we do end up with momentum conservation. So I shall clean down the screen and write this equation over here. Okay, so let's have a look at in S again. So in this case, the initial momentum, once again, we've still got them traveling in opposite directions. So just using this, we will have mvi over the square root
of 1 minus v squared on c squared minus mvi, because this one's going in the opposite direction, over the square root of 1 minus v squared on c squared. So still, these are equal and opposite, so they add to 0. And the final momentum is equal to this one, so this is the same but in the j direction. So we've got mvj over the square root of 1 minus v squared on c squared minus mvj over the square root of 1 minus v squared on c squared. So again, it's equal to 0, and these are equal to each other. So even with this new definition, the momentum conservation holds. So now we need to consider what's going on in S prime, which gets a little bit more complicated. So in S prime, let's calculate the initial momentum. So once again, ball B is at rest, so because that v is 0, it is not going to contribute to the initial momentum. We'll only need to consider ball A. So this will be equal to mv initial prime, that's this speed, divided by the square root of 1 minus v initial prime squared on c squared. Now we can calculate v initial prime using our velocity transform equations in terms of v. So again, this is just exactly what we did the first time. So v initial prime is equal to vx, which is the speed of this ball A in the initial frame in the x direction, so that is equal to v, minus u, and u in this case is minus v, it's the speed of ball B, so it's minus v, over 1 minus u, which was minus v, times vx, which we said was v, divided by c squared. So this is equal to 2v over 1 plus v squared on c squared. Now, to save ourselves some writing, what we're going to do is let beta equal v on c. So we can write this as 2v over 1 plus beta squared. So we will want to substitute this in here, but we'll also need to work out what this term is. So let's step through what this term is first. So this term is equal to the square root of 1 minus v initial prime squared, and we've just calculated v initial prime here, over c squared. So we can write this as the square root of 1 minus this thing squared, which will be 4v squared over 1 plus beta squared, and then we've got this c squared. So I'll put that on c squared, and why I've done that is now we've got a v squared on c squared here, so we can replace that v squared on c squared there with beta squared. So to help simplify this, I'm now going to give it a common denominator between this term and this term. So we've got on the bottom 1 plus beta squared, and then to get this on the bottom I needed to multiply 1 by that thing. So I've got 1 plus beta squared on the top minus 4 beta squared. So what I'll do now is I will expand these brackets, and I get 1 plus 2 beta squared plus beta to the 4 minus 4 beta squared over 1 plus beta squared squared. Now 2 beta squared minus 4 beta squared gives me minus 2 beta squared. So this thing here on the top is equal to 1 minus 2 beta squared plus beta to the 4, which you may recognize as that's 1 minus beta squared or squared. So I can write this as the square root of 1 minus beta squared over 1 plus beta squared. So this is equal to 1 minus beta squared over 1 plus beta squared. So that's now worked out what this term is. So we can now calculate P initial. So this is equal to M times V initial, which is this 2V over 1 plus beta, that's a beta squared. and then we want to divide it by this thing. So when we divide it by this thing, we can invert and multiply. So that's 1 plus beta squared over 1 minus beta squared. So you can see we've got 1 plus beta squared on the top and on the bottom. So these will cancel out, and we end up with this is equal to 2mv over 1 minus beta squared. Okay, so I'm going to write this here and then clear some space. So we've got P initial is equal to 2mv over 1 minus beta squared. And now I'll get rid of all this. Okay, so now we're going to calculate the final momentum in this frame here. So P final prime. Now we can use the same arguments for the x and the y components. Even with this form of the momentum, the y components cancel each other out. They're equal and opposite. The x components are going to be equal and they will sum together. So this will be equal to 2mv final prime, and we only need to consider the x component there, divided by the square root of 1 minus v final prime squared on c squared. Now, in the denominator here, this is not just the x component. This is the entire speed. So this is going to be a little bit more work. So we've got that v final prime is going to be equal to the square root of v final prime in the x direction plus v final prime in the y direction, and both of those squared. So this is just using Pythagoras' theorem to work out the total final speed. Okay, so to work out in the x direction, we will need to use this equation here. So we'll need to start by working out the final velocity in the x direction in the prime frame. So we'll want to use this equation here. So Vx here means the velocity in the x direction in the unprimed frame. So that's equal to 0. And then we've got minus u. Now u is the speed of the s prime frame along the positive x-axis. So that is equal to minus v. And then we're dividing by 1 minus, this Vx is 0, so it's 0. So this is equal to v. So that will go in there, and we will also need to work out the final velocity in the y direction in the primed frame. And to do that, we'll need to use this equation here. So Vy, that is the velocity of the ball in the unprimed frame in the y direction. So that is equal to v, and then we've got over times the square root of 1 minus, now u, that's the speed of this frame along the x-axis, so that's minus v squared, so that'll be v squared on c squared. And then this will be over 1 minus. Now we said before that Vx was equal to 0. That has not changed. So we can write this as V times the square root of 1 minus beta squared using this same definition of beta here. Okay, so now we've got these two components, we are going to substitute them into here. So this is equal to the square root of V squared plus this thing squared, which is v squared 1 minus beta squared, and then when we have the square root and we square it, we get rid of the square root. So this is equal to the square root of v squared plus v squared minus v squared beta squared. So we can pull the v squared out the front and it becomes a v. So that's v times the square root of 2 minus beta squared. So we've worked out now what goes in here. So let's now substitute in. So we've got p final prime is equal to 2m. Now v final x prime we've got over here. This is equal to v. And then we've got over the square root of 1 minus v final prime squared, which is this thing. So this is equal to v squared times 2 minus beta squared over c squared. So this is equal to 2mv over the square root. Now we've got v squared on c squared, so that'll be beta squared. So this is 1 minus beta squared times 2 minus beta squared. So this is equal to 2mv over the square root of 1 minus 2 beta squared plus beta to the 4, which you may recognize as the square root of 1 minus beta squared all squared. So this is equal to 2mv over 1 minus beta squared. And the initial momentum we've already shown was equal to 2mv over 1 minus beta squared. So using this new definition of momentum, we do end up with the final momentum being equal to the initial momentum. So now we can be happy because momentum conservation holds.